Let us try to understand how to find out the thermal resistance in case of the hollow cylinder. As shown over here, at radius R1 the temperature is T1 and at radius R2 the temperature is T2. So these are the boundary conditions. Now according to the Fourier's law, in case of the cylindrical coordinate system, the heat flow rate is given by minus Ka dt by dr. So R is the variable in this particular case. So Q upon A is equal to, so we have transferred this A on this side, so that is the heat flux is equal to minus K dt upon dr. Now transfer this dr also on the other side, so this Q upon A dr is equal to minus K dt. Now area, surface area of the cylinder is perimeter into length, that is 2 pi r. 2 pi r is the perimeter and L is the length of this particular cylinder. So Q upon 2 pi r L into dr is equal to minus K into dt. Now, as we have seen earlier, that the boundary condition is that at R is equal to R1, temperature is T1, at R is equal to R2, temperature is T2. So we are integrating this particular term, that is dr upon R and this dt, from R1 to R2 and T1 to T2 respectively. Now we know that integration of 1 upon R is log R, the limits are from R1 to R2. Integration of dt is T, the limits are from T1 to T2. So first substitute the upper limit. So the upper limit is R2 minus, in place of, so here it should be log R. So in place of R, substitute the upper limit, that is R2, minus, in place of R, substitute the lower limit, that is R1. Minus K as it is, in place of T, substitute the upper limit, that is T2, minus, in place of T, substitute the lower limit, that is T1. Now log M minus log N is log M upon N. So this log of R2 by R1. Take this minus sign inside. So instead of T2 minus T1, now it will be T1 minus T2. Now transfer this 2 pi L term on this side and log R2 by R1 on the other side. So it is 2 pi L K T1 minus T2 divided by this particular log term. We can write down this particular term in terms of temperature difference in the numerator divided by log R2 by R1, and this term will come in the denominator. So that again it can go in the numerator and you will get the same expression. Now we know that according to the Ohm's law, V is equal to IR or I is equal to V upon R, where V is the potential difference and R is a resistance. The same concept is applied over here. So here we are having, in place of the potential difference, there is a temperature difference. For current flow, it is analogous to heat flow, and the electrical resistance is analogous to this particular thermal resistance. So in other words, we are comparing this particular analogy over here. So this is the current flow, which is analogous to heat flow. This is the potential difference, which is analogous to temperature difference, and this is the electrical resistance, which is analogous to thermal resistance. So we can say that this is the value of the thermal resistance in case of the hollow cylinder. So Q is equal to T1 minus T2 divided by RTH, where RTH, thermal resistance, is this particular term. So we can say that in case of the hollow cylinder, the thermal resistance is given by log of R2 by R1 divided by 2 pi L. Now the same concept is applied in case of the hollow sphere also. Here also the boundary conditions are same. At R is equal to R1, temperature is equal to T1, and at R is equal to R2, temperature is equal to T2. So applying the Fourier's law over here. Now in this particular case, the surface area of the sphere is 4 pi r square. So it's Q upon 4 pi r upon r square minus K, and the limits are from T1 to T2. Now we know that integration of 1 upon r square is minus 1 upon r. The limits are from R1 to R2. Integration of dt is T. The limits are from T1 to T2. Now take this minus sign outside. So this minus Q upon 4 pi 1 upon r, R1 to R2, minus K as it is, this T and this limits as it is. Now in place of R, substitute the upper limit, that is R2, so this is 1 upon R2, minus, in place of R, substitute the lower limit, that is R1, so that is 1 upon R1. minus k as it is. In place of t, substitute the upper limit, that is t2, minus in place of t, substitute the lower limit, that is t1. Now this is nothing but r1 minus r2 divided by r2 r1. Now take this minus sign inside, so it is k into bracket t1 minus t2. Here also in the next step we have taken this negative sign inside, so instead of r1 minus r2 it will be r2 minus r1. And now we have transferred all these terms, so 4 pi r1 r2 and k will get multiplied to this particular term divided by this r2 minus r1 term. So ultimately we are having the heat transfer flow rate will be equal to, in case of hollow sphere, will be equal to 4 pi k r1 r2 t1 minus t2 divided by this r2 minus r1 term, which again we can correlate as we have already seen the analogous electrical analogy over here. So current flow is analogous to the heat flow, that is this I is analogous to this particular Q. Then potential difference, it is analogous to this temperature difference, and electrical resistance is analogous to this thermal resistance. So we can say that this is the thermal resistance in case of the hollow sphere. So we can say that this RTH, this thermal resistance, is nothing but R2 minus R1 divided by 4 pi K R1.